Have you ever stopped to think about what's really going on under the hood when you use a simple tool in Photoshop, like a sharpen or a blur filter? It feels instant, like magic, right? Well, it's not magic, but it's built on something that's honestly even cooler. Today, we're going to pull back the curtain on the hidden engine of digital image processing, filtering in the frequency domain. It's the secret sauce that makes modern photo editing not just possible, but incredibly fast.
So let's just start with that question right there. You've got a slightly soft photo, you drag a slider, and boom, it's crisp and clear. How on earth does a computer do that so fast? I mean, is it really looking at every single one of the millions of pixels and doing some crazy math with all of its neighbors? Well, kinda yes and kinda no. The real secret is learning to look at the image in a completely different way. All right, so here's the game plan for this explainer. First, we'll look at the old school way of doing things, pixel by pixel, and see why it's just too slow. Then we're going to get into the really mind-bending part, seeing images not as pixels, but as frequencies. After that, we'll check out the awesome toolkit this new perspective gives us, touch on one little glitch you need to know about, and then wrap it all up by seeing why this is such a powerful, game-changing idea. Okay, so let's start with what seems like the most obvious way to edit a picture. Just go through it one pixel at a time. This is called the spatial approach because you're working right there in the 2D space of the image. But as you're about to see, this common sense method has a massive drawback. So the technical term for this is convolution. The way it works is you basically have this little grid called a kernel, and it slides across your image, one single pixel at a time. At every stop, it looks at that pixel and the ones around it, does a quick calculation, and spits out a new pixel value. Now, imagine doing that for every single pixel in a 20 megapixel photo. Yeah, it's slow, it's clunky, and it's a huge drain on your computer's resources. And wow, this slide really hammers home the difference. The pixel-by-pixel method, that's the tangled mess on the left. It gets exponentially slower the bigger your image and filter get. But the frequency method we're talking about today, that's the rocket ship on the right. It is worlds faster, especially for big jobs. And this incredible speed boost is all thanks to a genius little algorithm called the fast Fourier transform, or FFT for short. Okay, now for the really cool part. What if I told you that an image isn't really a grid of dots? What if instead it's actually just a whole bunch of simple waves, all layered and added on top of each other? This idea, this radical shift in perspective, is the absolute key to unlocking the speed and the power of modern image editing. This whole concept comes from this guy, Joseph Fourier, and get this, he figured it out way back in 1807. He basically said that any repeating signal, no matter how complex and jagged it looks, can be perfectly recreated just by adding up a bunch of simple, smooth sine and cosine waves. You know, at the time, people thought he was a little nuts, but it turned out to be one of the most important ideas in the history of math and physics. And this right here is the perfect way to understand it. Think about a chord on a piano. You hear one complex sound, right? But it's really just a few simple, individual notes being played at the same time. It's the exact same idea with a signal or an image. You see those simple, smooth waves up top? Well, when you add them all together in just the right way, you get that complex, jagged wave down at the bottom. An image is just a 2D version of that same principle. And the mathematical magic wand that lets us jump between these two worlds, from pixels to waves, is called the Fourier transform. It takes a regular image and breaks it down into all of its basic wave components, or its frequencies. And what's so important is that it's a two-way street. We can use what's called an inverse Fourier transform to put all those waves back together and get our original pixel-based image back with absolutely no information loss. Okay, so we can turn an image into a bunch of frequencies. Big deal, right? Why is that so useful? Well, because now, instead of messing with millions of individual pixels, we can just tweak the frequencies themselves. This is where we get our amazing toolkit for doing things like blurring and sharpening almost instantly.
And the whole process is just beautifully simple. It's just 3 steps. Step 1, you take your image and, zap, use the fast Fourier transform to convert it into its frequency map. Step 2, this is the edit. You just multiply that frequency map by a simple filter. And step 3, you take that result and, zap, use the inverse fast Fourier transform to turn it back into a regular picture you can see. That's it. So elegant and, as we saw, so fast.
Now, the trick to all of this is just understanding what these frequencies actually represent visually, and it's pretty intuitive. Low frequencies, those are all the slow, smooth, gradual changes in your picture. Think of a big, clear blue sky or a painted wall. High frequencies are the exact opposite. They are the sharp, sudden changes, things like the hard edge of a building, the texture in a piece of clothing, or even film grain. So let's put it into action. This here is a low-pass filter. You can think of its shape like a smooth hill. It lets the low frequencies, which are clustered in the center, pass through, but it blocks or reduces all the high frequencies out on the edges. So what happens when you remove all the sharp change information from an image? Well, you get a blurred image. The filter literally smooths everything out by killing the detail. And now let's just do the complete opposite. This is a high-pass filter. See how it's shaped like a valley? It blocks all the smooth, low-frequency stuff in the middle, and it only lets the sharp, high-frequency information on the outer edges pass through. And the result? You're left with just the edges and the fine details of the image. This is the very core of how a sharpening filter works. You're basically boosting these high-frequency parts to make the whole image feel more crisp. Now, this whole digital process is incredible, but it's not perfect. There is a common glitch, a kind of weird side effect that can pop up whenever you're dealing with digital information. It's something called aliasing. To put it simply, aliasing is just a weird distortion that happens when you try to capture something that's really detailed, but you don't take enough snapshots to capture it accurately. If you don't sample fast enough, you miss key information, and your computer gets confused and basically invents a false or aliased version of what was really there. A common way this happens is when you shrink an image down because you're throwing away pixels, you're undersampling. You've definitely seen the two main kinds of this. The first is spatial aliasing. Those are the jaggies, the blocky, staircase-like edges you see on lines in low-res images. Or it's that bizarre wavy moire pattern you see if you take a picture of a TV screen or a shirt with fine stripes. The other kind is temporal aliasing, which happens over time. The classic example is the wagon wheel effect in old movies where the wheels look like they're spinning backward. That's just because the camera's frame rate wasn't high enough to capture the real motion of the spokes. So, okay, even with that little quirk of aliasing, it is truly impossible to overstate how much of a game changer this frequency-based approach has been. It didn't just improve image processing, it completely revolutionized it from the ground up. And what's really wild to me is the timeline. You have Fourier proposing this genius theory way back in 1807, but for over 150 years, it was basically just a cool idea on paper. It was just too slow to actually calculate for anything complicated. It wasn't until computers came along in the 1960s and someone discovered the fast Fourier transform algorithm that Fourier's theory was finally unlocked and became the incredibly practical, powerful tool that's inside almost every digital device we own. So let's bring it all home. What are the big takeaways here? Why is this so important? Well, number one, it is just ridiculously, unbelievably faster. Number two, in a lot of ways, it's more intuitive. It's easier to think, I want to remove the sharp details than to design the complex pixel math to do it. And finally, number three, it's just incredibly powerful. It lets us do really complex things that would be a total nightmare to even attempt in the pixel world. And that really just leaves us with one last big thought. We've seen how we can play with an image's frequencies to do things like blur it or sharpen it. But if an image, and for that matter, sound, radio waves, everything, if it's all just a collection of simple waves, what does that actually mean? What other kinds of realities, what other kinds of sensory experiences could we build just by editing their fundamental frequencies? It's something to think about. Thanks for tuning in.